So I'm bringing in, I'm getting real primitive, I'm bringing in paper notes because some of this is just easier for me to talk about from this perspective. So generalized matrix formulation, if we're going to call some vector input x, x sub 1 through x sub n characterizations, if we are going to formulate some sort of relationship between them, right, we're going to have some product relationship such that we would have the weights for the system, right, also vectorized W1 through Wn. We're going to treat this relationship, the dot product. You guys remember this one? Okay? So the dot product is going to be the successive process of x sub 1, W sub 1, all the way out to x sub n, W sub n for that characterization. If I write up an understanding, right, which previously we've described as the error characterization for the system, I'm going to take the relationship of the error output for the system, and I'm going to talk about the gradient of that relationship as some element j, and I'm going to characterize that relationship as 1 over 2n, right, for summation of n of the errors for the system components squared, right? What am I talking about? I there in that case. The index of the vector product components for this dot product characterization. When we said previously that error could be extrapolated out as d, right, sub I minus, we're going to call this d tilde, right, sub I. This is related to that error, or sub I of the system. This is the difference between what we expect to get and what we actually got, right? So, one of the critical assumptions we're going to have here is that as the gradient of the system drops across this representation, right, as we have some change in W, I really hate this, this is very, very annoying, right? Some change in W across the system, error is going to be expressed across this axis. We're looking at error to go down. All right, remember the relationship here is that the gradient for this error estimate is going to be an indication of the change of greatest magnitude, right? The direction of the greatest magnitude of change. So we're actually going to take the negative value of this system in order to traverse down this space. We're also going to be able to rewrite this orientation or this relationship of the system in such a way as to characterize it as, by large vector orientation or calculation, dot product of the vectorization of x sub I for this system. Thus there exists, all right, some initial weight consideration, some W initial, right, and then some secondary W, and then some W final for the output. We're going to call this W for this central position W star. This is just a specialized notation for our discussion at the moment. W star is the ideal set of outputs for the system. All right? So W star is a coordination, which I've discussed this previously, where the partial J with respect to the partial for biases for the system is equal to 0, and where also the partial J with respect to the weights of the system is equal to 0. Okay? What am I indicating there? When the gradient, when the relative slope of the incident of the error surface of the system goes to 0, I've done what? Maximize the function relative to the local error. So at any position along this system, right, as it's continuing down from either side of the values on either end of the weights, right, either a higher weight or a lower weight in the system, will eventually come to what? The bottom resting place. What happens to the gradient at that point in time? For simple purposes, the gradient is just relative derivative. So what happens when the derivative reaches 0? So when we're thinking about this from the perspective of learning rate optimization, I want you guys to think about it from the perspective to say that in any position on either side of this slope, I have gravity pulling me down. What happens when I get to the very bottom of it? Is gravity pulling me to the right or to the left? No. Gravity is pulling me just straight down. Thus, the process of weight optimization is going to be a process like gravity pulling us to the position in which there's no continued relevant update to the gradient J relative to the change in biases or gradient J relative to the change in weights. Most of what we've been talking about thus far is just the weight update process. We haven't really talked about the process of adjustment of biases, right? But it is part of the problem. And it is part of the problem because the bias, the offset from the center of the cluster data does make a difference to our fundamental calculations in the system, all right? We're going to go through now. I'm going to go ahead and start this up. And once again, we get to look at tons of numerical figures here. I'm going to turn this front light off. Okay, so we get a little bit better, contrast. What's the difference between the notation provided in this slide and the one we were looking at previously? Okay, I didn't have to look far. I did not have to look far. Let me explain to you that whatever I mean that they're all different, that means they're all different. Okay? But funny thing is, this one's actually a little bit more consistent with what I discussed originally than the one we looked at before. All right? The first slides in that set of slides that I showed you the last time uses an inverse naming process because there's a difference between the four-layer characteristics and the backprop. We'll get there because today we're going to look at the matrix formulation based upon the mathematics I just put up on the board. All right? This should have all of those calculations in it, but you're going to have to fill in the gaps of the understanding that our goal is to get from some weight matrix, that is the current value of the connections between the components of this network, and the weight matrix that should be ideal given the relationship between the I/O, the input and the output space. Now there's a couple of cool things about this example. This one I found online. I'll give you a link to it if you want to look through it because it has a few things that are in there that I didn't include in the slides. But what I did is I kind of chopped it apart and kind of showed you a couple of kind of key items to attempt to workflow it a little bit. We're going to use this notation for this particular incidence because I think it does an interesting job of showing that the weight is relative to the layer it is participating with, right? So the actual node itself participates in a slightly different process than the weights themselves because the weights themselves, several of them feed in to each of the nodes. So the node is a transformation, okay? And the weight is a transformation. The weight is a simple linear transformation of what? Just a scalar operation. Feature times scalar. So where does the nonlinearity come in? How do we make it nonlinear? How do we make it circular? How do we make it fit to complex functionality? The nonlinearities, okay? And these are the operations that run on the products of those linear scalar operations. Whenever I see the naming convention, I see W, okay, it says J2, right here's this middle one right here, J2, K3, right, what is that indicating? K is what? Destination, and J2 is what? Source node, okay? This one's simple because it doesn't include the source layer notation. It's actually, the whole layer in this case would be what? Would be called J or H1, okay? You could also say hidden one could be just node or layer 1. Interestingly enough, some systems make input layer 0, some systems make input layer 1. So once again, just pay attention to making sure we have continuity and that the naming convention maintains symmetry across the process. This matters because of the fact that once we get into the matrix formula, we're going to see which pieces we're bringing in, and sort of how we count, where we count to, where we count from. Now notice, across the bottom of this network, I now have the activations. So we're going to incorporate, this time we're going to be walking through it in matrix notation form, so I mentioned to you that we're going to do that. That is really kind of where we're going to stop, other than me going through doing derivations and proofs. And I will do those async, because it's easier for me to write on my tablet and show you the equation formulas. I actually have it all up here, okay? So all of these notes I carry around with me are all of my, this is my brain on the side that I have to have, because the notation for this is notoriously rough, all right? But hopefully this is going to stick with us to give us the full format. But we have 3 different activations here, and that's interesting, right? We used to maybe think that all the activations need to be the same, or would be the same, the output of the system. No. One layer can have its own activation, completely separate from, and for the intentional purpose of providing optimal results for the features that are provided in the space. So we're going to see 2 different methodologies of activations relative to weights, and we're going to see the contributions of how we're going to calculate that weight matrix product given in the system. Okay? So the first step in any training process, we're going to work with real numbers here, or at least not really going to work with them, all right, but there's going to be real numbers provided. If you need to see real numbers applied to this system, these numbers check out, at least for most of the stuff I was able to punch into my calculator. All right, so I'm roughly trusting the person online, which I know is a terrible, terrible thing. Right? Don't do that. But I'm assuming in good faith that they probably did, their homework on this and probably plugged it into the right places. Now, notice the notational characteristics. I have a vector of input and a vector of output. Vector of input is what? That's going to be my labels, right? My label function relationships, or excuse me, my feature function relationships and my target function relationships for the outputs. All right, so my labels are going to go on the output side, and my inputs are just going to be whatever pieces of information are going to be informing me about what the specific class that is intended for the output in this space. Notice 3 dimensions for the output, 3 dimensions for the input. Also notice something. What format does the output take in this particular case? Okay, it's vector, good. Why is it a vector? Because there's multiple output nodes, right? Mm-hmm. So if there were only one output node, then it would be a strict binary relationship. This is an interesting one because this is technically a 3-class classifier. Why do I say it's 3-class? Because this indicates that it is a member of class 1 or class 0 with this matrix, right? Because it shows that it is 100% aligned with whatever is present in that value. I'm just telling you this sort of off the bat, that this is a probabilistic assumption, okay? So the probability of being a member of class 1 as provided by this vector is 100%. It is 1. If there was a probability of it having multiple belongings or whatever else, that would be a totally different process. Let's imagine that there are 3 discrete containers. Container 1, container 2, container 3. All right? You put a ball, it goes in one of 3 boxes. This is what is often called one-hot encoding as well, if you've ever seen that terminology, is that the output vector corresponds to a series of output nodes. Each of that output nodes is effectively like a conveyor belt that leads off into each of the 3 boxes for the system. So each of those nodes is the terminal location such that whenever the appropriate weights are placed in here, this is W star, that is the ideal weight matrix, right? That whenever I times W star, which would be this whole sequence of workflow processes times activations, would ultimately end up doing what? Lighting up one and only one of the end neurons. Only one of the end neurons would actually be activated, and it would only be activated relative to the threshold of what we're going to call the softmax operator. Have you ever dealt with a softmax besides in machine learning? Besides machine learning? Where else?
Natural language processing.
Huh?
NLP.
Oh, well, that's still machine learning. All right, that's still machine categorization. So NLP is just a branch of procedural prediction, right? So it's just a I would say it's probabilistic mixed models. So yeah, it might work better in that sense. Okay. Notice here we've actually initialized these weights, meaning that they now have real values. So computationally, we can actually run this network through the feed forward. All I have to do is plug in the input, plug in each of the relevant contributions, right? And then I'm going to be able to calculate that product. So we're going to go through that process through both one feed forward layer, one calculation of the error output, and then the update process by which we're going to change all of those, hopefully a little bit closer to W star, to our ideal position where we have globally minimized our values. Now, do we know what that W star looks like? Do we know where the ideal balanced position for all of these weights are? No. You can think of each of these as coefficients in multiple different equations attempting to provide a structural transformation to the input data such that it transforms it to be the output data, each one of those assuming operational linearity. Okay? So the input relative to H1, the elements of H1 in, for N1, into N3, etc., right, are calculated relative to this particular node J1 and generate some output H1 out 1. We've noticed something. Those are not weights, right? Those are values being provided. So first H1 N1 is what? Going to be related to the product of I1 through I3 relative to the weight matrix. So the weight matrix that's being provided here is the weight matrix which would be the connectivity between vector I3 and that other product. Now, as I said previously, if I was to express this as a vector times the matrices, I can do it as an element-wise operator or the dot operative product if I have an agreement between scale of the components, right? So as long as there is an agreement between scale of elements, then I can utilize the transpose of I times W, the W matrix, and I can get my output product in the system. I'm going to also have to do another operation, and I'm going to keep reminding you of this operation. This is so this is probably one of the last times I step through sort of neural networks running forward in the class because I know it gets a little old, but I also want to make sure that sometimes by the repetition we get a little elucidation of the inner workings of the system. Why am I adding B's? B for J1, J2, J3. They're biases. What do they attempt to do? They
Adjust towards the mean.
They attempt to correct for the means of the distributions, right? Notice we have one for each of the integrators, right? So each integrator is going to have its own bias associated with it. Now, you can either have one bias for a whole layer, which is not necessarily advisable, right? Old systems used to do this because it was a lot easier to have one layer-driven bias. But most of the time, you're going to have one bias, and it says here, for each element, J1, J2, and J3, we're going to just have some scalar value that is simply added to the product of the input times the weight matrix. That is going to do, hopefully, once we calculate the distance between the means of the system, also be adjustable for the relationship. Where do I get the biases for this system? Are they calculated like we did in regression, based upon the distance between the mean of the distribution and each sample?
They're random to start with. Yeah.
Say what?
They're random to start with.
They're random to start with, just like the weights.
Yay.
Anybody seem like that kind of was like, huh? That seems, so everything's random? I just shook the box up really hard? Yeah, you just shook the box up really hard. We have no initial assumptions. No assumptions have been put in place based upon the data. The system is functionally 100% naive. All right, we're going to notice it by the level of error that we see in the system. Yes?
So I guess why not just start everything at a standardized value, like why random?
Yeah, why randomized?
Okay, this is really a hard thing to answer, but at the same time, not super hard to answer if I give you an analogy. So bear with me in saying that I'm not going to give you a mathematical solution to that answer, but I'm going to give you an example from the way I think about it. Procedural search processes, thus such as algorithmic search processes. So let's think about tree traversal, right? So you're in one position, your Roomba is in your house, right? Your house is divided up as a series of tiles. Your Roomba can go from any tile to any adjacent tile, and it wants to try to find the ideal pathway through the room, okay? As it traverses through each of the tiles, it's going to be able to see where the next tile is in the space. Whenever you have a discretized operational space, it's relatively easy to sort of prescribe an ideal traversal mechanism based upon greedy optimization. Go from the tile you're in to the next tile that seems like the best tile, given whatever the score metric is, right? Is that tile dirty? Do I need to vacuum it? Versus is that tile cleaner than the one I'm on? And then only go through the system, cleaning up the most of the dirt as it can while it's driving through its little path. This situation, that particular system is going to say that there is, in fact, one ideal pathway through your house that allows your Roomba to go all the way through the house using the least amount of power and cleaning the most number of tiles per charge per run through the space, right? There is one solution that is the best of all of them. Are you going to figure it out, right? Is your Roomba going to keep going through the house over and over again, shot after shot after shot, attempting to try to beat its previous speed record, right? Or is it just going to keep doing what it's done based upon its previous inference? It's going to work with an initial assessment, right, for key randomization. I'll explain to you the reason why I say key randomization. I'm looking for somebody in the woods, right? Where they are could be anywhere within the space. Where do I start looking for them? Do I start on the edges and walk through every single grid of the space of the forest until I find them, right? That seems a little bit unorthodox. That would seem poor. So what I might do is I might start off with an understanding of the space. That's a heuristic, meaning that I might start off with topology, all right? That's an assessment based upon the distributional characteristics of the data, but not an exact orientation or exact placement of that individual. So theoretically, starting from any position and fanning out from that spot has the same likelihood of finding the individual, right, as would the procedural search. Matter of fact, starting from any randomized spot in the forest could actually help you find the person slightly more quickly. We're dropping a whole airdrop full of people to each one look for their own ideal positions in the space relative to that current topology where they are at the particular moment. So the randomization is actually a methodology to attempt to reduce the search time by randomly seeding the initialization positions. Each time that you reinitialize the process randomly, you may actually converge to a different set of solutions. I don't like talking about this. Neural networks are not deterministic in any possible way. They are not going to find the same solution run after run, no matter what you do, unless you fix the seed of the initialization for the process. If you fix the initialization seed, you will notice something. The order through which the data points come through the system will also cause it to converge differently. So depending on how the data is presented, right, you can start a network with the same original initialization, same randomization. Depending on the order that you show it the examples in the data set, which should also be random. Why? Because you don't want it memorizing sequence. So you show it the order of the elements randomly. Notice what's also going to happen. The updates for the relative error for each sample at each unit time are going to be different. Different batches, different groups, different orders of systems are going to cause the system to converge and update in different ways. So neural networks are the ultimate sort of greedy, optimized, idyllic local shortcut. But they have a lot of disadvantages in the effect of saying that they aren't necessarily always going to provide you with W star, the ideal set of solutions for the output. So while we started off by talking about how we randomly initialize biases, I've gone off on a whole different tangent where you guys go, well, if this is all just random, I might as well just go home and just shake the box up. It's not quite as random as it seems. While each individual weight is placed at an arbitrary position relative to its weight surface. There is, in fact, a global minima, right, relative to error, and there are potentially several local minima. We're going to look at ways to overcome the local minima problem in the hope that if we continue training it over a long enough period of time, everything will eventually settle to the lowest possible points relative to that early initialization, the first initialization sequence. So while we start off randomly, the hope is that that random seed process, which is usually driven by a kernel that we know to be representative of standard spatial distributions, and that is we use Gaussian kernels to be able to initialize that. So the weights that are actually put into this weight system and the biases from that initial framework are actually seeded randomly from a zero mean Gaussian the normal distribution in order to create, hopefully, normal distributions of weight in the initial state. If I had one sort of set, predefined set of arrays and weights that every network started from, the problem is that there may be limits to that, such that I can't really restart it if it doesn't converge to the solution that I'm looking for. The problem with algorithmic solutions, all right, for those of you who have been in my 461, one of the problems with algorithmic solutions is what? Algorithmic solutions for fixed deterministic solutions for best case for the traversal methodology, right? If I was to have a hard algorithmic solution to go through every possible permutation for the system in brute force to find the ideal weights by brute force, what would happen?
Take too long.
It would slightly longer than we have, right? So the heat death of the universe would occur about 5 minutes before we were finished, all right? The reason why I say that is that you have exponential gain in time in order to be able to optimize whenever you have millions of free parameters, all right? So these systems, once they get up to complexity sufficient to us to be able to really use them for much of our modern problems, are just too computationally complex in order to approach at a full brute force level solution. So what we're going to do is we're going to have to find shortcuts that work well enough to give us good enough solutions that can be given in a reasonable period of time. The example that I give here is you're on a dock, right? I don't know if I'm using this example here. You're on a dock and there's a bunch of packages, right? There's a bunch of trucks backed up to the dock, and somebody comes up to your boss comes up to you and says, hey, can you write an algorithm that tells me which boxes to put in which truck such that they get there, right, in the fastest period of time they get delivered, plus the truck only has to go to a very narrow region of space so that we save money on fuel, right? We don't have to pay drivers extra overtime. You go, I got it, I'll be right back. You go upstairs, you write a brute force stacker solution that goes through all possible permutations of all boxes and all trucks. You come downstairs 6 months later and you go, I got your solution. And he goes, those left 6 months ago at 5 a.m. Like it's already done, okay? So we're really looking to try to find the solution that works best in the given time frame that we have available. A solution today that satisfies most of the constraints, but may not be as exact as a solution that we might like to have, is the solution that we're ultimately looking for by using this gradient descent, greedy local approximation methodology, all right? I know I went off on a tangent there, so let's get back to our calculations. What is the end product of this? It's H1 right, relative to what? H1 is the product of this matrix plus this. Now H1 has to then be, something has to be applied to it. So, I got to overlap between those. I'm not sure what happened there. Something got too big. Sorry. Fixed. We're going to run it through our nonlinearity, okay? We want to know what's actually coming out the other side of the node. The node is not a weight, but it kind of is, all right? And the reason why I say it kind of is because it's a summer and evaluator. So what do we actually have here? We say that H1 out is related to the max product of function ReLU max 0x, which is what? The rectified linear unit has linear operability to x at a value greater than 0, all right? But then is effectively 0 otherwise. Why do we do this rather than doing the sigmoid operation? We'll talk about it later on, all right? It has to do with conserving the gradient relative to the backpropagation process. A rectified linear unit allows the weight to actually continue to go negative, right? Or as the input to continue to go negative while not actually outputting any change in the activation function. So that means that this particular node, this neuron, can continue to participate in the process, can continue to receive a backprop update because it is now still valued, right? It still has real value components, but it isn't going into suppressed values of linearity below 0, and it isn't necessarily being completely zeroed out with respect to probability as it would be the sigmoid. So once something slides towards 0 with the sigmoid, it gets pushed all the way over to 0, which is probabilistic 0. It's going to be almost impossible to dig it out because you're going to have to find a reason why a neuron that's producing 0 activation participates in the backpropagation, right? So if it's not producing any activation whatsoever, then it's functionally useless. It's what's called ablated, meaning that it's been burnt out, it's died. So neurons can actually die via some backpropagation processes to where they're no longer updated. In some networks, this is a good thing because it actually creates what's called sparsity, which is a more efficient network, right? You have a neuron that's not participating qualitatively in the future process of the network, then get rid of it. It's not doing anything. Your brain actually does this, right? Neurons that aren't being activated will eventually die out because we don't want to keep them if they're not participating in anything. So they die out and our brain becomes more efficient because we have fewer neurons consuming resources. So the activation operation for the ReLU just is going to use 0 for operational output for as the integrated value of the output continues past 0. So we can calculate here the input times the weight array plus biases initialized here at 1, right? So this would just start off with an assumed everything is all the same in terms of operations. Biases can effectively be inferred arbitrarily. You can set a bias at 0, you can set a bias at 1, or you can randomly initialize it. All right? The reason why I asked that question is because bias is effectively entirely up to us. The kernel by which we initialize the weights is also up to us. Like I said, the tools that I'm providing you with where I say you can randomly initialize biases, you can randomly initialize weights, that is perfectly fine. And using the zero mean Gaussian assumption just makes it more likely that it would converge if the system is a natural system. Notice I've got real valued outputs from this. I have a vector here composed of components indicating that the current activation outputs for H1 through H3 of the system have these real valued outputs, right? Notice they're above 1. So what does that indicate? The last element, H3, has a value of 1.8. That indicates that the summation of the weights times, so the inputs for I1, the input layer, right, relative to J layer, ends up being what? J3 relative to what? This is X sub, the input layer I times the weight of IJ, right, IJ3, the weights for 2, node 2 of I, right, I2 through WJ. So this says summationally, I'm going to take all 3 of those weight sums and I'm going to scale it up to what? 1.8. What is that? What am I actually saying here? I'm not rescaling the input. I'm creating an output of 1.8. So the actual value that's going to be going into any of the weights that are in between this connection layer from here, the first input extraction is going to be that vector. So similarly to how this vector is with I times the weight array, the next layer in the system, right, for the relationship, times the ReLU operation is going to then be the output operation for HI processing. So the hidden layer, the first hidden layer, times I, the input layer, right, is given by this. Weights, input, bias, input to the activation, activation, inputs, so you notice in, and then out on the other side of it. The last segment here is that this is just a calculation of the actual numbers, and this is the actual output. So where does this go within our calculations of the next layer of the system? H2, the second hidden layer of the system, is going to do what? Where does it derive its inputs? The activations of the previous layer times the weights of the previous interconnected layer of the system. Notice the pattern is going to be retained pretty easily. H1 out comes from H1 out times the ReLU, right? So we already know what H1 out is. We know that the weight matrix is J to K. So we say that the layer of origin is closer to the weight and the layer of destination is farther away, right? So just all we have to look for is saying vector times matrix. How do we do this calculationally? You just tell your function to multiply this matrix times this way, right? So whenever we do I'm having my TA test the code that I put together for that exercise. I wasn't super comfortable with it because I did get an error with it once or twice. I think I fixed what was wrong with it. I was gonna have you guys just watch a video, and then the guy says some stuff in the video that I wasn't comfortable with. I didn't like it, right? It wasn't weird racist opinions or anything, but it was bad stuff, okay? So bad things as far as like overgeneralizations about networks and talking about things that really were not. Like I said, they made me uncomfortable, right? Where I'm looking at it going, yeah, but maybe not, all right? So this code still works, so I did most of this out of this code. So, what's this last portion? Bias again. We need a bias at every layer, so every layer is going to be adjusted for the offset of the distributional characteristics of its input. The output for this system, right, relative to the relationship of what? Input of the neuron, okay? So I'm going to then say that the inputs of each of those elements is going to be the summation of that product relationship. This one is going to go through, instead of the rectified unit, the sigmoid operation. Why use two different activations? Well, interestingly enough, sigmoid works pretty well for fast optimization, right? It will find and converge relatively quickly to good solutions, all right? So part of the reason why it was used originally is because probabilistic outputs are all automatically built in, because each individual output of that neuron already has the normalization between 0 and 1. So partially this was, original neurons did what? Basic binary classification, and they did so using sort of an analog output of the likelihood of the inputs to be correlated to that particular output. So the Adelaide, the single layer perceptron that just has inputs, weights, summation, and activation, right? This was the option they chose. Why didn't I put this at the previous layer? Well, part of the reason why I would put it closer to the output is that same relationship as I was talking with you beforehand, which is weight decay, right, and the propagation process. The further you go back in the network, the partial of the partial of the partial becomes what? Smaller and smaller and smaller and more distributed over more weights. So the value of the error, as the value of the error starts to converge towards an ideal limit, what happens as well? Those values continue to go down. We say that in general, this particular process is kind of a diminishing return within our training outputs, but also there's another significant problem here, and that is that as that system goes back, the gradient starts to do what is called a vanishing act, right? So we call it the vanishing gradient problem. So the further it chains back through the system, the gradients that are being propagated to the elements of that last layer are so small that if one of those particular activations was to get caught down here towards the minimum of the activation participation, what would happen? It's never going to be able to get pulled back up and be a key participant in the network. Once things start to settle in the network, we run into problems. There is a key life cycle to the training process in the network. Initially, the network has a lot of error to be able to correct. And then once most of the key bulk error has been removed by adjusting some of the parameters by larger values, what happens? Very little error remaining, and each epoch, each process through the forward cycling of the system will eventually start making it to where amount of learning, the amount of improvement per process, per sequence of this workflow does what? Produces less and less improvement in the overall product of the network. So this system will start off learning quickly and then learn much more slowly. Similarly to how we do. We learn big concepts early on in life, colors, shapes, things that are fundamental to the natural universe, and then later on we're learning little minutia, right, that might make subtle changes to the difference in our efficacy of certain tasks. All right, so these networks will start off very receptive and very capable of learning a lot of information, but then will slow over time. So by putting this activation, which may be more suspect, right, and may have a little bit less stability for longer term processes closer to the end of the system, we get the advantage of it at a higher learning rate, but we don't have a lot of the disadvantages of it being further back in the system, right? The further back in the system, we're going to want to try to use nonlinearities, right, activation functions that are going to map well to maybe being able to be rescued from gradient death, right, by small update processes. So, sigmoid operation, we take the output of the first hidden layer, right, we multiply it by the weights that connect hidden layer J to hidden layer K, which is hidden layer 1 to hidden layer 2, add our biases, and then we have the input of hidden layer 2, which is going to then be multiplied by the weights, right? We're going to continue the process. But the sigmoid activation here is going to relate such that the nonlinearity supplied here is 1 over 1 plus the natural exponential to what? Negative H2 in 1 characteristic. So negative H2 in 1 is going to be second hidden layer's activation property, such that the sigmoid operation will just return a quantity for each of these values that ranges between 0 and full activation. Notice the difference here in the output of the weights at this layer. Nothing's above 1, right? It can't be because the activation function doesn't permit it. So the shape of the output of the activation function will make a difference in terms of what the actual inputs of the second layer look like. So the first layer has activations that can go theoretically up to whatever, right, increasing in weight linearly, which means what? It means the system has increased learning capacity. Because the only information that's actually present here is going to be a representation of the data value between 0 and 1 based upon the relative accumulated action potential of that neuron, right? How activated it becomes by all of the data that is being trained with. Okay? The whole of the process is encompassed in this one slide, right? Such that if we want to try to understand the relationship between the input at the top times connectivity plus biases becomes the input for the first elements in the first hidden layer, right? Through the ReLU. Then the second, those outputs become the inputs of the weight matrix for that system. Then they get run through the sigmoid. Sigmoid outputs become the inputs for the third layer of the system, such that they are going to be segmentally updated. All right? Those are the outputs for the observation. Now the outputs are going to be related by something that we call the softmax function. The softmax function looks complicated up there, right? Ugh, that looks nasty. But keep your eyes on just the segment to the far right-hand side where it says probabilities. Because functionally, the softmax function is just a probabilistic assessment based upon the relative density of the output layer to the probabilities of each of the class as a function. This is a mapping function. We just say that each probability or each system of features being recognized at the output layer is then run through the activation based upon this relationship of multiple different nonlinear relationships for the class likelihood outputs. So there are J classes, J elements within the system, J probabilities, and each of these activations are Z's, the output of the activation assumption based upon several nonlinear relationships of the natural exponential. What are those? Probability density functions, right? So each one of the sets of features that are given at the output layer will be mapped to the likelihood of fitting one of the understood characteristics of the system. This particular system just gives you the probability that green, blue, purple, and red are the classes being effectively assigned to the output. If any of you have seen what happens in later deep learning networks, where we're doing things like multi-class classification, high multi-class classification, the final output layer is just a sequence of likelihood assessments for that particular set of features, indicating that that particular class would be the one given in the system. So something that could detect, glass, something that detects wheels, something that detects doors and door handles, right, might combine together and say, this is a car. So the composite of multiple layers of abstraction for representations become the relevant outputs and the intensities of the outputs for each neuron relative to the weights times the activations, finding that particular feature within that particular feature vector, that particular set of information encoded within the data. Okay, so sigmoid operation, we've already talked about that. Softmax operation, we've already kind of discussed this here. And in the end case, we're going to just have the output as presented here. What was the intended output? Right, something like 1 and 0, 0. Did we get close? Not really. All right, we got some errors, okay? Remember we talked about loss and cost functions. With standard linear operators, we could just use mean squared error estimate. That's what I put up on the board earlier, right? But whenever I get into the softmax functionality, I'm going to have to use this operation, okay? Which is going to be the cross entropy operation. All cross entropy means is the likelihood of one specific class relative to the likelihood of all classes in the system. Simple Bayesian probability, right? One versus the rest. So the likelihood of being within a class relative to the likelihood of all other classes within the space. Each of those softmax outputs is going to give you that operation, and the cost function is going to be what? The difference between how well the system did at providing the output for the target class versus this cross-entropy analysis of what it did for providing likelihood of all other relevant classes. So we're actually going to be using a multi-dimensional distance metric. Okay, that's crazy. We've gone into high dimensionality space. We're going to tell how far away the projected output was from the intended output of the system, utilizing this double integration of log likelihood assessment, right? Log of class assessment relative to class plus everything else, right, minus the class times log of 1 minus the assessment for that particular class in the system. Double summed across all the samples, double summed across all the classes, okay? The reason why I'm looking at this as all classes and all samples is the global error within the system is going to not be the error for one single sample, it's going to be the error across the entire run of all of the samples and all the outputs, right? So thus far we only have one sample and one output, right? But we're going to utilize cost function analysis. I'm going to talk about this real quick, and that is cost functions may be complex, meaning that one cost function can actually have two different operations based upon two different levels of error. So in one case, we might have a cost associated with the participation of members of class y equal 1, and another cost operation for y equals 0. So if we can represent the system as a piecewise operator, we can actually have different costs for different classes. Go back to the analogy about the grenades and apples problem and what happens. Different cost for different scenarios, and thus we can have the model incentivized or penalized more strongly or less strongly depending on what we consider to be the overall cost of that specific type of error within the system. So we can actually assign arbitrarily externally that something that is a real interesting target class, right? That would be detection of cancer. We would want to not miss cancer. So what we would do, we say anytime that you miss cancer, we're going to penalize you more highly than whenever you miscategorize something that isn't cancer as cancer. So we're going to push that discriminant, we're going to push that line over into the space where we're going to make sure to maximally capture the target class, which is going to be based upon cost assessment. We do probabilistic cost assessments, or we do cost assessments based upon arbitrary connotations, okay? So arbitrary connotations are going to allow us to do what? Previously, we're calculating J theta, or the gradient for the weight update system, based upon unified mean square error cost. Now we're actually going to be doing it based on what? This more complex cost function. So how do we do that? We just plug in this cost function where we were previously plugging in that grad J calculation. So instead of just doing the simple grad J calculation, we're going to do the integration of the calculation for this function, right? That is the one that provides us with an assessment here. We can generalize it as just a generalized nonlinearity, and what does that ultimately end up being for us? Similar to the previous homogeneous update system. So we say, relatedly, some learning rate times the integration of the error. So the integration of the error is going to be multiplied by a learning rate, and the weight is going to be updated, the current weight is going to be updated to the next successive weight in the system, theta j prime, right, based upon theta j at the current moment, minus the update for some specific weight operation, right? So we're going to go through this for the other weight system. Output for this system has already been calculated, and we note that there is a difference between the operations. Once again, this classification space is what? Categorical. So what happens to the output? Do I say sheer binary, IO, right or wrong? You got the wrong hot? No. I'm going to have to calculate the relative distance of the specific output I had for the softmax to the target class, right, to the target classification output. So categorical cross entropy in this particular case is going to be 1 over n samples in this consideration for each of the 3 outputs for the target times log of the output component for a component sub I, right, times 1 minus y sub I times log output of all other potential output classes, right, so the non-targets. What do I do with this? Calculate it. All I have to do is plug this into the formulation in order to get my output. At the end of the system, I end up with what? An error calculation, okay? Previously for nonlinearities, we did this for MSE. Now, like I said, all I'm doing is I have 3 categories. I have one category that's the desirable category. I have the distance between that and the output, as well as the distance between the desirable categories or the non-desirable categories and the assessments that were given for the non-desirable categories, right? The system gave us that it was 0.26 for category 1, the desired output was 1. It also gave us that it was 0.32 for desirable 0. That is a type of error in and of itself, right? So the fact is it was positively valued in the class we didn't want it to be. So that means that the weights are going to have to be updated, not just to try to figure out how to make 0.26 more 1, they're going to have to be able to be figured out how to make 0.32 more 0. So we're going to be doing all 3 of these simultaneously, and the relative error assessment given down here for the log likelihood assessments for class likelihood outputs based upon the softmax output of the system indicates what? Total error in the system is about 0.98. That's really high, okay? Meaning that our initial seeded values, terrible. Our first guess was really, really bad, okay? But we have a guess, okay? Important derivatives. These matter because of the fact that if you're going to actually calculate the reverse process, you're going to have to push it through the filter of the derivative of the operation, the nonlinearity operation you put it through. Am I going to put you through calculating that nonlinear operation? Not really, okay? The reason why is we could go through and derive these, and my predecessor does. I consider it to be maybe mildly busy work, all right? The reason why is because it does test your math skills, but at the same time, I'm not really sure it helps you learn a lot about what's actually going on here. because it's the workflow of the network, not your ability to do something like, the reciprocal of 1 over log e to the negative x, right? So I don't remember what that is. It's like log of something over 1 of something log something else, okay? It's rough, all right? There's a whole big sequence to get from there to there. But if I know what happens in the end, and I know actually the partials relative to the components of the system, then I can just utilize these expanded polynomials as substitutions for that derivation. So now I have a mathematical equivalency that I can substitute in place of that valuation whenever I'm doing the backpropagation cycle. So, hidden values for backprop layers, right? For any given layer, the error for the error of the partial for one input of the system relative to the output is what? Going to be the distance between the desired log relative to the output of the system. So in general, I can write up this system for -1 times y times 1 over the output 1 plus 1 minus y1 target characteristics times 1 over 1 minus the output in case 1, all right? This is for one weight. Remember what we did previously with our grid calculations, and we said we had to prop through the weights? This is just one prop weight, already given the relationship by canceling the partials. So I've propped through the system already to be able to determine weight from the most immediate output through the first nonlinearity, right? This is the nonlinearity output, right? And then I've propped the output of that system for the weight matrix of the system relative to that activation. Now, one of the things that's cool about this is, remember we had similarity and we had symmetry on how we put together the weight output calculations? The symmetry is going to stick with us, such that the first output for weight of K1L1, right, or excuse me, yeah, K1L1 for the system can be written as the partial here, right, E1 to out1. The second weight, right, W2, which would be E2 relative to out2, can be given, once again, and out3, likewise, okay? Notice something. Those are all effectively the same equation. What have I done? Change the indexes. So once I derive that initial equation, once I derive that initial relationship between how the activation plays a part in the weight propagation process, that the activation is going to do something on the weight, it has a portion of the error, plus the weights themselves need to be updated as a result. So the weights relative to the activation of the system, we need to adjust the weights such that the activation of the output is ideal. So we go from W, some W, to W star in this case. Numerically, I've calculated the output for this particular relationship product, so I can give you the relative error of each individual weight as it proportionally integrates to the error of output 1 in this one specific system. Now, remember, if I continue through the process, I can utilize operational symmetry for the derivatives of the space, and I can continue to write operational symmetry for the entirety of the output, okay? One extra minute here. If I go through this whole thing, I end up with what? One output activation relative output of K1, L1 for N1, okay? Continue the matrix products. I can see out 1, N1, out 3, N3, out 2, N2, okay? Each of these are the matrices of the relevant scale contribution of the errors for each of the systems. If I know that W of some KL, L1 is related to the partial of the error with respect to that weight, then all I have to do is calculate the relative error of the weight via the chain rule to backpropagate it, right? And I know that the partial with respect to weight K is also a matrix that I can calculate as the product of the error times the weight products. I can do what? Calculate this bad boy, okay? That look nasty enough for you? Once again, what is it? A bunch of matrix products. Easy things that we know how to calculate real quickly within mathematical frameworks. What mathematical frameworks am I talking about? Python, okay? That's the only mathematical framework I care about in here. We know that we can get the thing to do this quick because this is procedural, right? It's a procedural process. So even something as complicated as figuring out the relative contributions of each of the input weights as it relates to the partial of one weight in the system. You have a variety of final weights in the system contributing to what? One update for the ultimate weight of the system can be calculated as a product relationship, and then I can then see all weights in the system such that I have full output weights, right? IJ can be updated, and I now have what? The relationship here indicates how much each of the weights needs to be changed, right? This is the new adjusted weight value of the system in order to attempt to optimally, based upon those partial gradients of each of the backpropped elements in the system, that's how much each of them needs to be adjusted in order to be able to ideally find the next solution. How do we then go about this? We do the same process over again, okay? And we wash our hands, we start over again. Next time we start, okay? I'll put these slides up for you guys to go through, and I'm going to also be doing the expansion of the proof of the universal approximator as a video for you along the way. Hopefully by the time we get to Thursday, we'll have your assignment in Python. We're also going to be doing a write-up derivation assignment where you'll be doing something similar but not quite this level of complexity to be able to write it up yourself, to be able to see if you've got it in hand, okay? All right, thank you guys. I appreciate the extra couple minutes. I'm sorry about the late start today. See ya. For this, I'm gonna put my hands. No.
Okay.
So, I don't know how, but I've been trying to figure out, I figure out things better. So, basically, I wrote out the simplest thing I could think of, just taking the one single input from
Okay.
and so I have like two nodes that are, so they have two weights.
That's a good question,
So
actually.
what does this look like?
Yeah, I can draw it out.
Yeah, I mean, we're gonna be. Yeah.
Okay.
And then node.
Well, that's what I was asking, that's how long.
No, it's a.
I didn't put
It's a giant star. It works.
I didn't put a third weight
Okay.
because, you know, you have one.
Is that a
It's doing the
appropriate level of
validation.
complexity for your task?
You have a test train and validation.
Yeah.
It's doing the validation.
works.
Okay,
So yes.
It's an appropriate level of complexity.
Unless it gets stuck.
No, it's not.
No,
But I'm okay with it. It just works. All right.
So the thing that's confusing me is, so when I'm doing the back propagation,
Oh, never mind.
I understand that.
I don't think this class-
What? It's for a research.
And so essentially, you're subtracting the value from the weight. You're taking the.
Yes, so you have the
It doesn't have a
weights.
date on it.
Let's say,
I
this
think
is
it's
the
sorry.
third
Validation.
Yeah,
I know it looks
minus
weird.
some updated
It makes sense that
value
no one else is here, right?
Anyway, I would call it 5:30. I'm gonna go.
So it's like the derivative of the law.
Time.